Okay, so let us continue. Now he'll close that, he'll join the cope and drag so we can pour the molten metal.
And we need to ensure that there is no loose sand. A good way of doing that is to blow, and it's sensible to pop on a pair of goggles to make sure that nothing blows back into your eye. So that is the basic mould produced. We just need to produce the core to lay across so that we can form the hole through the middle of the casting. We use the two-part block, introduce sand, poke it down and ram it to give it some strength. Make sure it's full, trim the top, and then by giving it a tap, it should release the core, which you can carefully lay across the prints. The two halves go together, again just checking for loose sand, locate a pin, put it together, and that's ready for pouring. Because we're going to be using molten metal, we better have a bit of health and safety going on. A leather apron that saves any splashes to the body, suitable gloves, and finally a full face visor to keep things nice and tidy. So after a break of 5 to 10 minutes, we now have a pot of molten metal. I'll just turn the burner off. Nice long tongs so that I'm well away from the heat. Just rest it, move the tongs down, and then pour the metal into the pouring basin so that it gently flows. The top of the metal is slightly convex when you first pour it, but as things cool down, the casting contracts, the metal will feed in, and we'll see that it becomes concave and dips in the middle of the runner. It may be that you need to provide surplus metal within the mould so that it will keep feeding. You might have to add maybe up to 50% more metal to the mould than you're going to use in your final casting. Okay, so we've let the mould cool down for 10 or 15 minutes. So hopefully, when we open it up, we'll have the magic of a decent casting in there. It's filled well on the bottom part of the mould. Because we've only used a low temperature metal, the sand hasn't really been compromised. We can now break out the casting. It is still hot. You still have to be remembering that it will hurt you if you pick it up.
You see, that is our final product, but those all other components that were there, sprue and your gating system, runner, etc., all those have also been solidified, right? So we have to remove that. So just so that we can have the actual component. Okay.
And then we can just take the sand from the core, just poke that out, and there we have the hole right through the casting, and it's come out and quite nicely aligned on the joints. We just have to cut the sprue off, and that can be remelted for the next job. There's very little waste in the foundry industry. So now we're going to look at die casting. This is a nice simple.
Right now he's showing die casting. We might see it some other time, right? Now let us see all those different parts, okay, and what are their functions. Is that clear? Any doubts from that video? Is riser not provided in this? I believe. One second. Riser. Yes, I think riser was not there in that previous uh, video that we saw, right? We'll see. I'll make you show another video. You can even see it from here, and I'll tell you what is the reason why we are giving the riser. Okay. So all these different components that you see the terminology we have. The pattern, as I said, we can call it an approximate duplicate or true replica of the required product of casting. The approximate duplicate because I told you the reason just now. It is an approximate duplicate and not an exact duplicate. Why? Because you see, I told you we have to give allowances, right? Plus or minus. Either you have to keep it larger than the required casting or smaller than the required. Right? Dimensions increase or decrease. Right? That's what. So that is why approximate duplicate, or you can call it a true replica. It exactly resembles that, right? Size may be different, but the geometry is same. So pattern is that. Okay, flask or box, as I said, rigid metal or a wooden frame that holds the molding material. So that entity where you are putting in those sand is called a flask or a box. Cope, the top half of the molding box. Drag is the bottom half of the molding box. Core, object that is inserted into a mold to produce internal features of a casting, such as holes, or there could be ribs, etc. Right? If they are required, then I'm sorry, not ribs. There could be holes or slots, right? Slots. So that is what core does. Okay, you can place different cores. So basically, where you don't want the material to get filled in, you use core. That is the basic idea. Okay, or you can call it internal features to produce internal features. You see riser. Where is exactly the riser? Here. Let me use slideshow. Right? You can see here. Once we have poured in the metal, right, and this cavity is filled, how to ensure whether the molten metal is full and is filled completely inside? Once it is filled inside here, it will come here and then rise here, isn't it? So I'm sorry, here. Yes, exactly. To know the mold is filled, that is one of the reasons. Okay, I'll tell you other reasons also. So this is where you are filling in. Okay, this is not the riser. This is the riser. Okay, I was confused. So once this starts filling in, right, and this cavity is filled, and if it goes full here, and then it will rise, right, from here, so that we can know the mold is filled. That is one reason. Other reason. So we know what a riser is. Okay, where is it now? You see a vertical opening in the mold. Okay, it acts as a vent for gases also, right, to escape for the escapement of gases, right, to prevent air gaps. Okay, right, because if the gases don't release, you will have air gaps. Helps to confirm that the mold is completely filled, right? That's what we discussed. Acts as a reservoir of molten metal to feed and compensate for shrinkage during solidification of a casting. You see, when the molten metal is solidifying, you'll have shrinkage, right? That's the property. When it goes from liquid to solid, you have a shrinkage, so the dimensions would reduce. So what will happen is that mold which is filled, that molten metal which is being filled in will shrink. Okay, so the dimensions would reduce, right? So who will ensure, what will ensure that that filling of the material, okay, of the what do you call, that gap which is there because of the shrinkage. If it shrinks, the dimensions reduce and you have a gap there, right? So that will not be exact. You'll have it of the what do you call, a lesser size than the required casting. So we have to ensure some component which will fill in, right, which will take into account that shrinkage. Once it is shrinking, there should be some component which is supplying the molten metal, so that you can have the exact, that gap is filled because of shrinkage, right? Is that clear why that riser is there? That you remember that word. I mean, wherever I'm highlighting with colors, that indicates your keywords basically. Okay, that helps you to remember as well. And those are the main points, you can say, main reasons. Okay, all throughout the slides. Okay, this is not just one slide. All throughout the PPT, all those which are colored, okay, or bold are important, right? General common sense. Explain last point once. Okay. Wait. You see, the last point, it acts as a reservoir. The riser is responsible for supplying the molten metal back to the mold cavity, right? Why? Because of shrinkage. There is shrinkage as the metal is as the molten metal is solidifying, there is shrinkage. So the dimensions of the component would reduce. It will shrink. It will, what do you call, the dimensions would reduce. For example, a circle, right? A sphere basically, not circle, sphere, right? If it is of this size, right, when we have poured in that metal, once it is solidifying, it will shrink. Let me draw it with another color, right? It will be maybe of this dimension. Okay, I'm showing an exaggerated view. It will not shrink this much. Okay, so the dimensions would reduce. So there has to be some component in the system which will supply that molten metal back, so that this cavity is filled. Because of shrinkage, you have this cavity, right? So that cavity can be filled again with the help of this riser. Is that clear? Okay, okay. Okay, so that is what your function of the riser is. And then the gating system. Okay, the sprue, runner, all these gates also, it comes under your gating system. These are the channels used to deliver the molten metal to the mold cavity, right from the pouring basin, right? You have all these entities which are responsible for taking that molten metal to the mold cavity. You can have a simple definition of it. All the channels which are used to deliver the molten metal to the mold cavity. What are the components in the gating system? You have sprue, the one we discussed, right? The one he has made with that tool he had, right? Vertical passage in the gating system. That cylinder what he used, right? For example, here you see that's the sprue which is responsible for taking this molten metal. You also have pouring basin, okay, but it is not there as a general, uh, not considered as a general component. That is why it is not there here. Or maybe here you see pouring cup they have mentioned. So after the pouring cup, it goes through the sprue. It's the vertical passage here, and you can observe that it is not straight. The cross section is varying. You have a larger cross section here and a smaller cross section here. Observe. So it just says it's a vertical passage, but the reason, can you guess what is the reason to keep it tapered, having a higher, a larger cross section here and a smaller cross section here? What could be the reason to keep that change of cross section? To prevent erosion? No. It will prevent erosion in some form, but how? You see, this is based on fluid dynamics, and basically the principle of casting is based on this Bernoulli's principle, right? Change of pressure difference is what is allowing the molten metal to flow, isn't it? Direct fall will not be there. Okay, if you see, even though we have kept tapered, if you keep it straight also, it will fall directly. If you keep it tapered also, it will fall directly. Then you see, let me give you a hint. When that molten metal is coming down, okay, the velocity here and the velocity here are different, isn't it? You have a lower velocity here. As it goes down, because of this acceleration due to gravity, you have increase of velocity here, right? So here you have a lot of velocity, isn't it? It has gained this what do you call, because of this vertical height here, it has gained that velocity, isn't it? So the velocity here is more. So you tell me, based on this discharge, what is the formula for discharge? Area into velocity. If you remember, you have learned this fluid mechanics, right? Fluid mechanics and hydraulic machines. Yes, A into V, area into velocity, basically area of cross section into velocity. So you see here the velocity is less, okay, and you have some particular area. But once the velocity is increased here, to have the same discharge, you have to keep a lesser cross section, isn't it? That will maintain the same discharge. If not, what will happen is, if you keep the same cross section, that velocity, because of the increase of velocity, there will be air gaps here. The air, I mean, uh, it will create a vacuum, and that will attract the air, okay, because that's the general principle, right? When there is vacuum, it will attract the atmospheric air, right? So that will go along with the molten metal. So you have air also going in along with molten metal. Then that's what we don't want, because that will create gaps in this mold cavity. So to avoid that, you keep it tapered, right? Let me draw it here. If you keep it tapered, the higher area here, A1, and velocity V1, the velocity has now increased here, V2. So naturally, to have the same discharge, you have to have a lower area, cross-sectional area. So that is why it is reduced, to maintain the same discharge and to avoid this air gaps. Okay, I mean, to avoid air coming in along with molten metal, you have to have a tapered cross section. I hope that is clear. Okay, fine. So that is a sprue, and then it goes through. The next part is called runner. Okay, once it exits the sprue, what you have next is called a runner. RUNNER, runner. So that runner is responsible for stabilizing the flow, because you see there is a lot of turbulence now because of that falling of the molten metal here, right? Even though you have some erosion and there is turbulence involved, but when it comes here inside, it is still turbulent. To have it stabilized, you have to use that runner system. That runner is basically of a constant cross section, just so that we can have that stable flow, right? The turbulent flow is now being stabilized. Is that clear? That is your runner, and once that it passes through the runner, then we'll make it pass through the gate. Okay, basically a gate, as he mentioned in the video, it allows the molten metal to come inside the mold cavity. That is why you call it the gate, and there could be many gates, depends on the size of the casting. We'll see in some examples in the next slide, hopefully, that you have several gates for large castings, so that you can have multiple entries for this mold cavity. I mean, this molten metal to flow into the mold cavity, you have multiple entries and therefore multiple gates, right? So that runner, gate, as I mentioned, horizontal channel used to stabilize the molten fluid is your runner. Gate, which connects the runner and mold, right? It acts as a gate, as simple. And that is your those two, cope and drag, aligning pins, right? All those you have seen in the video. The reason why I'm making you watch those videos is it will be easier to understand when we are looking at the diagrams and the matter in the PPT. It will be easier to understand when we see demonstrations, isn't it? So sprue pin he had used, isn't it, with the help of that cylinder. So you see pouring basin, sprue, and then you see skim bob, basically to avoid to have that, because once the velocity has increased, as I said, there will be erosion here, right? You cannot avoid that. to take that eroded soil here and to take any slag or impurities, this skim bob is provided. Here you are seeing, right? Let me show it with red color. You see, that is a skim bob, right? So that will take the impurities and any other eroded soil because of this increase of velocity in the sprue, right? And then it goes through the runner and gate all through to the mold cavity, and then the riser. I've already explained what is the riser, right, and what is its function. So it plays exactly above the mold, so that we can know that the mold is filled. First reason. Other reason, it will supply when the shrinkage is happening, right? Is it clear? Okay, so that, I think we are done with. Yes, it's already 12:10. We'll see the advantage in the next slide. I mean, in the next class. I'm sorry. Any doubts in today's class? Because this is what you will be seeing all throughout. The reason why I am spending more time here is because it's totally about casting. So if you understand one type, it will be easier to understand the other types. So no doubts. If there are no doubts, then we'll end the meeting. Okay, then if there are no doubts, then we'll end the class. Thank you.